Well, here we're going to cover today in this video discrete random variables and cumulative distribution functions. To motivate this concept, let's start with one example. Consider the sample space when tossing a coin twice. If we toss a coin twice and we register the sequence of outcomes as one, the sequence of what we can observe in the two tosses, if we register that as only one, then the sample space is this. We can observe head in the first toss, tail in the second one, tail in the first one, head in the second one, tail, tail, and head, head. So that is the sample space when we toss a coin twice and we register as we count as an outcome the sequence of the two outcomes that we observe in the two tosses. Now, I will define a function. Define a function that by now I'm going to call x, capital X. This function will have domain on the sample space. And the range or codomain, codomain is going to be a subset of the real numbers. If you don't understand the notation, don't worry. Only try to remember what a function is from your pre-calc course or calculus course. But this notation is not going to be very important. This one, this particular notation for functions. But the point is that x is a function. A function, I recommend to think of a function as a relationship between two sets. Yeah. In our example, x is going to count the number of heads. So I'm saying that we have a function from the sample space and a subset of the real numbers. This thinks is the real numbers. Real numbers. But what it is exactly? Well, this means that for each outcome in the sample space, we're going to have associated one value for x on the real numbers. How do we know what that value is? Well, pay attention to the description of x. X is going to count the number of heads. So we're going to count the number of heads in each outcome. For example, well, I'm going to create a table, outcome of S, and the other one X. Then for the outcome HT, how many heads do we have? We have only one head, right? So the value for X here is 1. And for the other ones, TH, TT, and HH. Here, how many heads do we have? We have 1. So we put what? In the next one, tail, we have no heads, 0. And in the next one, head, we have 2 heads, so 2. So you see, we have a relationship between the sample space and some subset of the real numbers. In this case, the subset from with the number 0, 1, 2. But each outcome has associated one value in this set. But the point is that a random variable essentially is the outcomes in the sample space. They have certain relationship with numbers, with some numbers. Like in this case, because x is the number of heads, the relationship of these outcomes with this one, with the number 0, 1, 2 is this one. All right. And we can also write without a table. For example, you want to say x of ht. This means what is the value of x when the outcome is ht? You look at the table and you say it's only 1. What is the value of x when the outcome is hh? This means only 2. Remember, this is similar when you cover pre-cal or calculus course. This is we had functions or f of x, g of x, and we said when we were evaluating the function at one value, at one number, we said f of something. Well, this is similar to that. For example, if you had f of x equal to x squared, and you want to compute f of 1, then you raise 1 to the square. So something similar is here. For example, if I want to compute, I want to know what is x of ht. Well, it means what is the number of heads for the outcome ht is only 1. Okay? All right. Now, based on this, I'm going to define other function. This is going to be lowercase p. That is going to be, now the relationship is going to be between x and the closed interval from 0 to 1. And this is going to be p of x equal to probability of the value of capital X. Be careful here. Here I'm trying to say x as a capital X or uppercase X, and this one is supposed to be lowercase. So be careful with that. I know that it's easy to get confused because in the way here in my notes, I mean about what is the right notation, but there is a difference here between lowercase x and capital X. Lowercase, capital. But most of the times I think because of the context is going to be understood. But the point is that lowercase x is one particular value for capital X, and capital X is the variable. I mean, the thing that is grouping all the values. The point is that we are defining a function like this, p of x equal to the probability of the value of x. So for example, in our example, I mean this example, this one, take into account all the possible values for x. The possible values for x, they are 0, 1, and 2 only. What about if I apply this function, lowercase p to 0? P of 0, what is the meaning for that? The meaning for p of 0 is, or p of x in general, is probability of the value of capital X. In this case, the value for capital X is 0. And remember that all the values for x, they are 0, 1, 2. So this means that we have p of 0 is only the probability when x equal to 0. The probability when x equal to 0. How can we compute the probability when x equal to 0? Well, pay attention to where this value for x is coming from. This value for x is coming only from the outcome tt. If we have a fair coin, what is the probability we observe tt? Well, we have 1, 2, 3, 4 outcomes in the sample space. It's going to be only 1 out of 4. So the probability for x equal to 0 happens only when this occurs. So the probability is 1 out of 4. 1 out of 4. What is the probability for 1? This means what is the probability when x equal to 1? When x equal to 1, it is coming from ht and th, two outcomes of the sample space that has 4 elements. So it would be 2 out of 4, or 2 divided by 4. And finally, what is p of 2? P of 2, the probability when the x is equal to 2. In this case, the only possibility for this number is we observe head-head. Head-head is only 1 out of 4. We have a fair coin. So this means that this is 1/4. This thing, all of this, is called the probability distribution of x. Of capital X. So the purpose of the random variable in general is that we don't focus so much on the sample space. Sometimes, many times, we don't care. Our main interest is not precisely in the sample space. I mean, for a given person, maybe that person doesn't have any interest about to know what is the sample space or how to count or how to get the sample space. Maybe that person is worried or interested in other more precise questions or points. When you toss a coin twice, this is the sample space. But maybe for a given person, it's going to be more interested only on what is the probability that I observe one head, or what is the probability that I observe two heads. Well, these questions can be responded by using the probability distribution of x. Yeah? So in summary, we have x and the probability. The values for x, they are 0, 1, and 2. The probability here is 1/4, 2/4, and 1/4. I want you to notice two things with this. Know that, first, p of x is always positive. Or maybe sometimes it might be even 0, but, well, I don't remember one example where it could be 0. No, well, in this case, maybe, but in our example, notice how that p of x for any value of x, I mean 0, 1, or 2, always is positive. I mean, always has it returns a positive number, 1/4, 2/4, and 1/4. And notice that in our example, p of 0 plus p of 1 plus p of 2, this sum is equal to 1. If you add 1/4 plus 2/4 plus 1/4, we have 1. These are properties of probability distributions for random variables. And this property is going to be important to identify that we have a probability distribution later. I mean, these two properties. Next. Now, once we have the random variable, let's say that we can compute probabilities. Once we have the probability distribution for x summarized in this table, now we can compute probabilities. For example, let's say that I ask you, what is the probability that we observe more than one head? Remember that x counts the number of heads here. So a very precise question without knowing anything about the sample space is I want to know the probability of observing only more than one head. Well, in this case, you go to the probability distribution in this one here, and you will have to count the probability for the values of x that are greater than 1. In this case, the only possibility is the probability that x equal to 2. So probability of x is strictly greater than 1 is the same as the probability of x equal to 2. And this probability is only 1/4. What about the probability of x greater or equal than 1? Well, in this case, I have to take into account the probability of 1 plus the probability of 2. And I stop here because I don't have any more values after 2. If I had 3, for example, here, I would have to include 1, 2, and 3 because it says probability of x greater or equal than 1. So now we have this. This is 1/4 plus 2/4. And this is 3/4. So we can say, what is the probability, when tossing a coin twice, a fair coin twice, what is the probability we observe at least one head? 3/4, or approximately, well, I mean 75% probability. You see? Now, in general, the probability mass function or probability distribution function of a random variable is defined by E of x equal to the probability that the random variable is equal to lowercase x for all the values of x. And of course, if x has values x1, x2, and so on, then the probability that for any xi should be positive, and probability of x1 plus probability of x2, and so on, this sum should be equal to 1. I know I have said that we have a discrete run. Oh, I didn't write it, but I should have written this as a discrete random variable. What is a discrete random variable? Well, don't worry so much about it, but when we see continuous random variable, I'm going to point out the difference between discrete and continuous random variable. By now, it's okay if you have understood this. we know that we have a discrete random variable if it's probability distribution or probability mass function. If you check a book, maybe you're going to find it in this way: probability mass function or probability distribution is defined in this way for any value of x, and it satisfies two properties. The probability always is positive, and the sum of the probabilities over all the possible values for x should be 1. Now, associated to this, to probability mass functions, we have cumulative distribution functions. And this is defined in the next way. This is capital F of x, lowercase x, is equal to the probability that capital X is less or equal than x. This is the cumulative distribution function. So the cumulative distribution function is only other function based on the probability mass function or the probability distribution that computes the probability that capital X is less or equal than any of its values. Remember, this is lowercase, this is capital X. Capital X means the variable, all the values, and lowercase x represents one particular value of capital X. In our example, remember we had this, the table X, P of X, 0, 1, 2. We have 1/4, 2/4, and 2/4, and 1/4. What is, for example, f of 0? F of 0 is the probability that the random variable is less or equal than 0. This means only the probability that x equal to 0, because we have nothing beyond, below 0. And this is only the probability of 0, and this is only 1/4. So capital F of 0 is only 1/4. What is f of 1? F of 1 by definition is the probability that x is less or equal than 1. Less or equal than 1 means 1 or 0, because the only possibilities for x in this case, they are 1, below 1 is only 0. So, but this is this inequality, this symbol means, remember, that we have to include 1. So this is the probability for x equal to 0 plus the probability of x equal to 1. And this is only p of 0 plus p of 1. And if you check the table, 0 plus 1 is 1/4 plus 2/4. 1/4 plus 2/4 is 3/4. F of 1 is 3/4. And finally, what is f of 2? F of 2 is only the probability that x is less or equal than 2. And notice, what is the probability that when we toss a coin of a fair coin twice, what is the probability that we observe two heads or less? Two heads or less. That probability has to be 1%, right? I mean, this is the probability of x equal to 0, plus the probability of x equal to 1, plus the probability of x equal to 2. And this is p of 0 plus p of 1 plus p of 2. And this is only 1/4 plus 2/4 plus 1/4. And this is only 1. So this is the CDF for our example. By the way, community distribution function, many books is going to be identified as CDF. So maybe cumulative distribution functions, they have many advantages. One of them is that they can be actually defined over all the real numbers. I mean, with domain of the real numbers. I know it's, how can we do that? If in our example we have only the values for x equal to 0, 1, and 2, how could I define this function over all the real numbers? Well, in the next way. We can define capital F of x equal to 0. Notice the lowest value we have in this example, and we are in the same example, it's 0. So nothing less than 0. So we can say that this function is 0 for any x less or equal than 0. The other value, the next value is 1/4. I mean 1/4 here, 1/4. Oh no, I'm sorry, not less or equal, strictly less. I'm sorry. The other value when x equal to 0 is f of 0 is actually 4. 1/4, I mean 1/4, 1/4. 1/4, f of 0 is 1/4. So f of x is going to be 1/4 if x is less than 1 but greater or equal than 0. When x equal to 1, the value is 2/4. So we can say here it's going to be 2/4 if x is greater or equal than 1 and strictly less than 2. And finally, it's going to be 4/4 or 1 for any x greater than 2, greater or equal than 2. And notice how in this way we have defined a function with domain over all the real numbers, yeah? For example, defined in this way, based on this definition, we could compute any real number. For example, what is f of 1/2? F of 1/2 falls here, right? No, here between 0 and 1. So the when x is in this range, the value is 1/4. 1/4. What is f of negative 10? Negative 10 falls in this case, x less than 0, in this case only 0. And so on. Yeah. Most of the times, the cumulative distribution function is going to be expressed in a function like this, this is a piecewise function. All right, let's see one example. Example, it says here, let x be the ages of the students in a class. Given the frequency distribution, we don't have exactly the probabilities, but we have the frequency, so we can compute the probabilities. F of x above, determine the following probabilities. For example, what is the probability that x is less or equal than 22? Less or equal than 22. It is f of 22. In this case, we will have to consider all the values from 22 and less. So we have to consider 22, 21, 20, and 19. So it's going to be the corresponding probabilities. They are, well, we don't have it, here we don't have the probabilities, right? We have the frequencies, but we're going to fix that quick. They are not probabilities. Remember, probabilities must be between 0 and 1, and obviously these numbers are greater than 1, 12, 2, 6, 8, 2. But no problem. If you do the sum, +12 +2 +6 +8 +2 is equal to what? Is equal to 12 +2 14 +6 20 is +8 +2 is 30. So f of 22 is going to be all the frequencies less or equal than 22. I mean 12, 2, 6, 8. 12 +2 +6 +8. But if you want to convert this into a probability, divide by the total number, 30. And the answer is going to be 28 divided by 30. If you compute this, you will realize this is the same as this. Strictly greater than 20. So in this case, we have to count the frequencies for the outcomes greater than 20. This is 20, so greater 21, 22, and 23. Count the outcomes, I mean the frequencies, 6, 8, 2. So it's going to be 6, 8, 2, 6 plus 8 plus 2 divided by 30, and it's going to be 16 divided by 30. And if you compute this, you will realize this is equal to this. Finally, greater or equal than 20. In this case, it's going to be the same as before, 6 plus 8 plus 2, but you have to include the 20 in this case. The 20 is the value of the frequency for 20 corresponds to 2. So plus 2 divided by 30. And this is what? This is going to be 18 divided by 30. And this is the answer. This is part A, part B, and part C. You can verify that these answers are the same as these ones we have here. All right. So that's all for this video. See you in the next video.